Hi everyone, my name is Daniele Ragni and I work in Aeroacoustics at TU Delft. Together today, in this lecture, we're going to see the basics of aeroacoustics, the metrics, and the difference between sound pressure level and sound power level. Let's start. The course you chose is about aeroacoustics. That means you are interested in how aerodynamics can generate sound. In aerodynamics, we will soon learn that the most common ways to generate sources of sound are through mass injections or ejections, turbulent flows, or by unsteady aerodynamic forces on surfaces. Now, every transfer of energy is carried out with some losses. You are maybe already aware of friction losses or thermal losses, but some energy is also dissipated with the impulsive change of motion that you are imposing to the fluid that you are bringing with you. Now, in these 3 short videos, a special visualization technique, which is sensitive to the gradients of density in the flow, is used to show you what really happens, for example, when you clap your hands, drop a book, or make a balloon pop. Now, pause the videos, go back 10 seconds and try to freeze the moment in which the perturbation is generated and propagated to the far field. Well, as you have probably noticed, a perturbation is usually generated at the moment of the impact, which travels with a finite speed through the air and in all directions. Now, we still don't know how the perturbation is generated, but we know that once it is, the information it carries propagates in the far field. And that's why, in this lecture, we focus on the propagation of sound. One of the simplest acoustic examples to explain sound propagation is the one of the vibrating membrane. Now, if we replace for a moment an aerodynamic source with an effective membrane moving the flow back and forth, we can understand how the flow is propagated. The inward and outward motion of the fluid is transferred to the surrounding air molecules, causing a series of consecutive compressions and expansions in the fluid. While no fluid particle moves very far from its surrounding, information is still transferred through local collisions. Now, this perturbation or vibration in the fluid, which locally changes the properties in time, can be assimilated to a traveling wave. And typically we define sound as the part of the perturbation that we can actually hear. Now, let me ask you, what do you think is propagated with sound? Are the fluid particles going somewhere? Well, not really. The only thing that is propagating is indeed energy and information. Think about waves in a rough sea. While the energy is actually transferred through the ocean, the local fluid particles just move up and down. Here it is exactly the same, with the only difference that the waves are longitudinal waves. In other words, to transfer energy, the fluid particles move in an oscillatory motion, creating a series of expansions and contractions. We define the speed of the propagation as speed of sound, which by the Newton-Laplace equation reads as the square root of the isentropic bulk modulus divided by the density of the medium. In gases, the radicand simplifies as the incremental pressure variation per variation of density in isentropic conditions. For ideal gases, this is the product of the heat capacity ratio with the specific gas constant and the local temperature, or as you most probably know, gamma RT. As a curiosity, the pressure fluctuations we are referring to are typically very small in comparison to the ambient pressure. In the human audible range, therefore between 20 and 20,000 oscillations per second, or Hertz, the max variation of pressure fluctuation from a whisper to, for example, loud painful music is only about 200 Pascal, which is quite small with respect to the 100,000 Pascal of your barometer. Now in engineering, we recorded the sound as pressure in time. By removing the mean pressure, we can actually determine a pressure fluctuation time series, as we call it. One common way to measure the overall amplitude of such fluctuations is the root mean square value, which is representing the square root of the arithmetic mean of the square values of the fluctuations over time. As you can see from the equation, squaring the pressure fluctuations allows you to account for both positive and negative fluctuations as equally important, and the final square root doesn't do anything else than bringing everything to the units of Pascal. You might be already familiar with the spectral decomposition of a signal into its frequency components. We won't bother you with the mathematical details of such a decomposition, but it's still very useful through the course that you know how to transform your signal from time to frequency and vice versa, such as that the total energy of the signal is conserved. When we examine some spectra, we can distinguish between tonal contributions, broadband contributions, and narrowband contributions. Because the human hearing is not equally sensitive across all frequencies, we often weight the signal. The most common approach is the A weighting, which adjusts the spectrum to better reflect human perception. In this case, measurements are reported in decibel A or dBA. The sound pressure level is just a metric used to typically transform pressure fluctuations values onto a logarithmic decibel scale. We are only concerned with the fluctuating components of the pressure, not the ambient static pressure. The sound pressure level is usually obtained by taking 20 times the logarithm of base 10 of the ratio between the root mean square of the pressure fluctuations and the reference in air. In air, the reference pressure is 20 micropascal at 1 kHz, which corresponds to the threshold of hearing. To put this into perspective, fluctuations might range from a few times 10 to the power of -4 up to several pascal. Remember that the ambient atmospheric pressure is about 100 kilopascal, much larger than these fluctuations. We remind you that, because of the large range, we use the logarithmic decibel scale. The sound pressure level is calculated from the root mean square of the pressure fluctuations relative to the reference pressure. Remember this, 0 decibel corresponds to the hearing threshold at 1 kHz. And as you can see, with 100 decibel values, we can cover a range of several decades and therefore different applications. Here are some common values for you. Soft whisper is around 30 dB. Inside an average office, about 50 dB can be found. A vacuum cleaner at 3 meter distance is 70 dB, and a noisy factory can be around 90 dB. A jet engine at 100 meters corresponds more or less to 120 dB, and the threshold of pain is just above that value, typically around 140 dB. Note that the sound pressure level always depends on the distance from the source, as the root mean square of the pressure fluctuations does. It is important to distinguish between sound pressure level and sound power level. The sound power level characterizes the total sound power produced by the source in watt. The sound carries very little power. The reference value is only 10 to the power of -12 watt. So let's summarize the properties of sound pressure level and sound power level. Sound pressure level is dependent on the distance. It's not a property of the source. Sound power level is a property of the source and therefore doesn't depend on the distance. For a spherical source in air, doubling the distance results in a decrease of 6 decibel in SPL. Here, the amount of power that is actually generated from the previous activities in terms of watt of acoustic power. As you can see, we restate it once more. It will be quite difficult to even try to estimate the actual power generated through the sound for conventional activities. Let's try some exercises together. Let's consider the noise of a jet fighter. Its sound level is about 175 dB. A human shout is about 75 dB. So how many people shouting we need to match the noise of a jet fighter? As you can see here, by equaling the square of the PRMS of n amount of people shouting to the one of the jet fighter, you can retrieve your n. And the answer is essentially the entire world population shouting at once will not be able to match a difference of 100 decades. Now consider two sound sources, each producing a sound pressure level of 80 dB at the same location. The total SPL of the combined system lies between 83 and 86 dB, depending on whether the sources are incoherent or perfectly in phase. For incoherent sources, the total increase is about 3 dB. For coherent sources or aligned in phase, it increases by about 6 dB. You could try to be very rigorous and write the full formula for two generic waves and try to simplify it. We have done this for you. In case of perfectly out of phase waves, the result will be total cancellation. For choirs, you will get 4 times PRMS square, corresponding eventually to a factor of 10 log 4 or 6 dB. And for incoherent sources, you will get a factor of 10 log 2 or equivalently 3 dB increase. In practical engineering application, you can also find easy conversion tables which allow you to subtract or add sound levels, for example to correct for background noise. Suppose a turbine shows 55 dB with operation and 48 dB installed. The real turbine contribution would be, if you actually check the table, about 54 dB.
That's all for the current lecture. Pause the video, go back to those concepts which were less clear, and I hope you enjoyed it. And see you in the next lecture.